All right, so today we're going to look at section 6.3, volumes by slicing. And our basic idea, our basic goal is to ask the following types of questions. And we're going to jump right in there with some examples. Suppose that I had some function. Maybe this is the function y equals e to the x. And I took this region right here. Let's go from 0 to 5. I took this region and I rotated that region all the way around the x-axis. So I took this and I just spun that, I took this little shape and I spun it all the way around the x-axis. And if I do that, then what I'd end up getting is something that looks sort of like this. Right, so we get, let me look at it from the other direction. We get this e to the x. We get a funnel type shape by taking this and rotating it around the x-axis. And so our question is, what's the volume? Right, so if we have some shape that we can get by having an axis that we rotate it around, we'd like to be able to come up with a method of determining the volume of that shape. All right, so let's look at what we've got over here. We'll look at this general shape, and so this is called volumes by slicing. Our basic idea is to take our region, to slice it up into different pieces, to look at the volume of those little pieces and add them all up. Right. So suppose that I slice this off. Right. So we're thinking about our funnel shape here. And I slice it off right through with some plane going right through here. We'll see that we'll get a circle. Right. So the circle that we get is exactly what we would get if we took this this small line and rotated that line around the x-axis. So if we rotate that line around the x-axis, then I get this circle that behaves like this circle over here. Notice that the radius of that circle is exactly the height of the function. And so the radius is equal to the function height in this case, which is just e to the x. So at this given x value, the radius is e to the x. All right, so let's keep that in mind, right? So now our idea is to take our shape. We're going to slice it up into a bunch of different things, which are going to look like, instead of our whole shape, we're going to take pieces of it. So let's look at this again in a little bit more detail. Here's e to the x, and if I rotate this around the x-axis, and this is the shape that I get. So I'm going to take this small little piece and rotate that around. I'm going to think about thickening that. Right? So let's thicken that up, and what we get is we get a cylinder type shape, a small, thin little thickened circle, which is actually a cylinder with a very small height. Okay, so suppose that this how thick this is we're going to call this delta x. Delta x is the thickness of our slice. The height of the slice is the same as the radius of the circle. So pi times r squared for this piece is pi times the height, which is the function height, times e to the x squared. That's the radius, that's the area of the circle. But then when I thicken it by delta x, what I'm going to get is the area, or the volume, in fact, the volume of a small slice. And so I get a delta x here. So I'm going to write this as pi times e to the x squared times delta x. That's the volume of this small slice of thickness delta x. Now, as x moves along, if I think about moving along through the beginning to the end, well, the heights are going to change. Right? So that if the heights are going to change, we're going to think now about making at a different x value, we'll still have the same delta x and a slightly thicker cylinder. So at this x value, we have a slightly thicker cylinder, or it's going to be a greater volume because the radius is higher, but our thickness is still delta x. And our idea then is this: we're going to add up all of our volumes of the slices, but our volumes are pi times the radius, which is the function height squared. That's pi r squared multiplied by delta x. And then we add them up as we move along. Right, so as delta x, we can choose different delta x's. And if we make delta x smaller, we're going to have a better approximation to the actual volume because we'll be able to fit more of them in there. Right, so what we're really looking at is the limit as delta x goes to 0 of this mess. And we're going to not go through all of the details of this again, but if you remember, this really is a Riemann sum from Calc 1, and it really is, by definition, the integral. A limit of a sum as delta x goes to 0 is an integral of pi times e to the x squared. Delta x becomes dx when we write it as an integral, and in this case, we're going to integrate from our first x value, which was 0, to our last x value, which was 5. Okay, and so this is actually our answer. Again, we could evaluate that integral. This was actually e to the 2x, so we could integrate that. But for right now, I'm actually just going to worry about focusing on setting up our integrals rather than evaluating the integrals. So let's look at that in a different example. We don't have to go through that whole process every single time. I could just say something more like this. What if I have this function square root of x, and I want to take the region bounded by the square root of x, the x-axis, the y-axis, and x equal 4. I want to take this region and I want to rotate it around the x-axis. And what's the volume? It's the same idea, the same idea. If I take at a generic x value, the height is square root of x, which is the radius of the circle that I get when I rotate it around. So I'm going to get pi times the function squared, that's my pi r squared, and then multiply by dx, which is delta x, which is our thickening factor, and then I integrate from 0 to 4. And so this is the integral that would give you that volume. Okay, so how about something that looks like this? Let's go with square root of x still, and let's go with y equals x. And now I'm going to just rotate this region around the x-axis. So what we're going to get is sort of a bowl shape. If we took this y equals x and rotated around, think about how that would create it would create a top type shape. It would create a cone. So if we take a triangle and rotate it around, we get a cone. But so we've actually got the outer piece, that parabola, rotated around to make a bowl type shape, and then we've cut out the middle cone because we're not including the whole piece. But our idea here is that we can calculate the volume just using that exact idea. I can calculate the volume of the bowl, which would be integral well, I guess we first need to know what is this. Well, this occurs at x equals 1, because that's when y equals x intersects y equals x squared. So I'm going to need to integrate from 0 to 1. If I wanted the bowl without that triangle in the middle cut out, then I would have pi times square root of x squared dx. Pi r squared integrated across the region in question. Now we need to also take out the middle piece, which means I need to subtract what I would get if I would rotate the inside piece around. So that's 0 to 1, pi. R in this case is the y equals x, so that's just x squared dx, which can be written as integral from 0 to 1 of pi times square root of x squared minus x squared dx. So you can think about it as top function squared minus bottom function squared, or you can think about it as our original description, as finding the first volume and then subtracting off the second volume. Let's look at that same region. Here's y equals x square root of x, and here's y equals x. Same region, but now suppose that I want to integrate it, I want to rotate it around the y-axis. Well, from the last section, we saw what the first step ought to be. If I want to rotate it around the y-axis, I first need to figure out what y values we're using. Well, this is still y equals 1 right here, because it's at the point 1, 1 when those two curves intersect. So we're going to be integrating from 0 to 1, y equals 0, to y equals 1, dy. Right, so y is our variable. But when we integrated dx, we had x inside, which means I need to have y as inside as well. Y is my variable. And so in this case, I need to take both of my curves and solve for x instead. This becomes x is y squared, and this becomes x is y. Right? Now though, which curve is the top curve? The top curve, when I rotate it around the y-axis, is actually y equals x, which means I'm going to have pi times y squared, that's pi r squared, minus, oh, let's put this pi outside of the parentheses, minus the bottom curve, which is, in this case, y equals square root of x, which is x equals y squared, squared. Remember, it's pi times r squared. And so this is the integral that we would use if we wanted to rotate around the y-axis. Okay, that's the basics to get you started on 6.3. Check out the homework. See you next time.